Swayam Prabha. Digital India. Educated India.
So, in today's class we will go on with our interactions with regards to dipole-dipole, right. And in the last class what we actually derived was this expression where, so V is equal to mu 1 mu 2 by 2 pi epsilon 0 r cubed, right, where these are the respective dipole moments of the interacting dipoles. Let us take a very general case. What I mean by general case is the dipoles can be orientated with respect to each other at specific angles. So, what do I mean by that? For example, I have a dipole moment mu 1 in this case, right, and I have another dipole moment say mu 2. Now, this is, if I take it from the center of these two dipoles, let this be the distance between the two centers, which is r. So, you can understand what is going to happen with respect to the distance between the two dipoles. These dipoles are not parallel, right. So, they are maintained at a certain angle. So, this is angle theta 1, which mu 1 makes with this radius vector, and if you look at this dipole, then this makes with this one an angle theta 2. Okay. So, this is a very general case now. You do not know what angle it is, you are just trying to derive it for two dipoles oriented at certain angles. So, here we will not look at the derivation, but we will just write down the actual form. The actual form is, or the potential energy is, can be written as V is equal to mu 1 dot mu 2 by 4 pi epsilon 0 r cubed, that is the first term, minus, now this, remember there is a dot product mu 1 dot mu 2, that means we are talking about vector quantities now, right, minus 3 mu 1 dot r times mu 2 dot r over 4 pi epsilon 0 r to the power 5. Okay. So, this interaction energy can be derived, and we will not go into the derivation. Again, keep in mind the term on the right hand side, you can see you have mu 1 dot r, mu 2 dot r, and you have r to the power 5 term at the bottom. Okay. These are essentially your dot products of a dipole moments with respect to the radius vector r, which is the distance in between mu 1 and mu 2. Now, you know this definitely, that I can write mu 1 dot mu 2, now these are the vectors I am talking about, is equal to what? Mu 1, right, mu 2, then the angle between the two dipoles, right. So, I can write cosine of theta 1 2, that means there is an angle between the two dipoles, and remember this, when I am writing this like mu 1 and mu 2, these are the absolute magnitudes I am talking about. So, now these are scalar quantities. Similarly, if I can write mu 1 dot r, what should I be writing? I should be writing mu 1 r, then cosine of theta 1, right. So, all these again are vector quantities, please remember, and if I am writing mu 2 dot r, then this is equal to mu 2 r cosine of theta 2. Okay. So, again these are your absolute magnitudes. So, from now on what I will do is I will not represent them like this form, I will just write mu 2 r and all these things straight away. See, if I am having this and if I am putting this back into my original expression, then I have V is equal to, you can write mu 1 mu 2 cosine of theta 1 2 over 4 pi epsilon 0 r cubed, and the next term then becomes 3 mu 1 r mu 2 r cosine of theta 1 cosine of theta 2 over 4 pi epsilon 0 r to the power 5. So, again I have just plugged in these dot products, right. This theta 1 2 is what? Theta 1 2 is the angle between the two dipoles. Now, please keep that in mind. So, theta 1 2 is the angle between the two dipoles, and obviously theta 1 and theta 2 are the angles that these dipoles make individually with respect to the r which is separating them, the distance. And just there is an overriding here. So, this is essentially cosine of theta 1 and cosine of theta 2. Okay. Now, this thing can be further simplified, as you can see. So, this remains like this. You can see throughout you have a mu 1 by mu 2, mu 1 times mu 2 4 pi epsilon 0 term common I can take out. Now, not only that, you see now what do you have out here? You have r and r, which is essentially what? R squared. You have r to the power 5 term here. So, what I can write this one as for the simplification. So, V is equal to mu 1 mu 2 by 4 pi epsilon 0 r cubed. Then what should I be writing here? Cosine of theta 1 2 minus 3 cosine of theta 1 times cosine of theta 2, right. So, this is the most general expression you can have for two interacting dipoles making certain angles theta 1 2, theta 1 and theta 2 respectively, the definitions as we have discussed. Now, let us take a very specific case. Okay, let us take a very specific case. For example, let us take a case where I have two dipoles like this. These are two dipoles, right. So, I can have this one as say q1 minus q1 and this is q2 minus q2, and you can understand. So, this dipole has its orientation such that the positive end is close to the negative end of the other dipole, right. So, this is your mu 1 and this is your mu 2. Again the length is given as L, same for here, the length is given as L. Now, remember what distance we were talking about. So, this distance is again from the midpoint of the dipole. So, if I can extend my r, so this is your r, right. So, this one makes an angle theta, and this one, if you can understand, this one also makes an angle theta. Do you get that? So, this one makes an angle theta, that means mu 1 makes an angle theta with the radius vector r or the distance vector r, and this one also makes an angle theta, that means theta 1 is equal to theta 2. So, here I can say theta 1 is equal to theta 2, that is 1. Now, tell me what happens to theta 1 2? Theta 1 2? 0. So, theta 1 2 is 0 now, and if you put these here, what are you going to get? That means I can get, now I can simplify my V further by writing as V is equal to mu 1 mu 2 4 pi epsilon 0 r cubed, right. Then what is my first term? Cos 0 is 1 minus 3 cosine square of theta. Have you ever seen an expression like this before? What have we seen? But anyway, this is one of the places you can see in this expression, and this expression also comes in a very important feature in fluorescence spectroscopy, which is called Foster resonance energy transfer. There also we talk about interacting dipoles which are point charges, and there this orientation also comes in. Okay, but again, keeping this orientation in mind, right, where theta 1 and theta 1 and theta 2 are equal, these are parallel, theta 1 2 is equal to 0, you have this. Okay. Now this is an expression, guys, you will have to remember. The base expression, which is the one we started with, this base expression, that means the expression we want to start with, this you do not have to remember, at least I will provide this with you in the exam. Okay. But any further simplifications based on this expression, you will have to be able to do that. Now what do I mean by that? Let us take another case now. So just simplifying this further, we can take another case where we can have the dipoles like this, right. I can have the dipoles like this. So this is say mu1, this is mu2, again R is from the center, right. Yeah, you can have this, it does not matter what it is. And this is your R, okay, there is your R. Now tell me, what is theta 1 equal to theta 2 here? 90 degrees, okay. What is theta 1 2? Same, again parallel, 0. Now so what does V of R become now? Let us look at this expression. 3 cosine of theta 1 cosine of theta 2, what is cos 90? 0, there is also 0. So this term cancels out, I mean this term goes away. What is this? 1, good. Now think about this, I just be careful about the sign now. You see these are like charges, right. I can have q1 minus q1, right. I can have q2 minus q2, because I am keeping the convention of this sign of the dipole moment, what direction the dipole moment will be going. So if that is the case, what should the sign be? Should this be attractive or repulsive, you tell me? It should be repulsive, yeah, it should be repulsive, right, because you see q2 is close to q1, which are both positively charged ends, and then q2 is close to q1, which are again negatively charged, the negative ones. So this one would be mu1 mu2 times or over 4 pi epsilon 0 r cubed. And the interaction is repulsive in nature, because your like charges are just on top of each other. So think about the different orientations you can have, okay. Now think about the different orientations you can have. So I can take some other orientations examples, right. So one of the other orientation is this one just flips to give you a very stable interaction potential. When this one will flip, that means minus q2 would come here and this plus q2 would go there, what would you get? You would be getting a same thing with a negative sign, because it is a attractive potential, it is an attractive potential, that is why. So based on this I can have the following, simple cases. So what are the cases? I can have two dipole moments aligned like this, right, what we just saw. So this is mu1, this is mu2, and this is again R. So this we saw is what? Repulsive, right? You can see both are pointing in the same direction. The next one I can have is something like this, mu1, mu2, again separated by distance r. This is attractive, okay. I can have another orientation like this, which is I have something like this, which is one dipole mu1, right, and then I have another dipole which is like this is mu2, and again so distance to the center is r. Now here you have to tell me, would this be attractive, would this be repulsive? My hunch is, and this you have to figure out yourself, there would be no interaction. You understand why, right? There would be no interaction. What is theta 1 2 here? What is theta 1 2 here? It's not 0, it's 90 degrees, right? Because you extend it like this, it's 90 degrees. So what is cosine of 90? 0. Okay? And then you can figure out how it comes out, right? So I have already given a hint. These things in the exam you should be able to figure out by yourself and write down the respective interactions, right? So what are the two other simple cases we can have? So continuing with our cases, we can have two dipoles like this, right? So this is mu1, this is mu2. So would this be attractive or repulsive? This would be attractive, right? Or I can have this one, again mu1, mu2. So R is essentially from the middle, this is R, okay, again here this is R. So this would be repulsive, okay. So the bottom line is, for all these simple cases you should be able to figure out what the interaction potential V is, okay. This you should be able to figure out. So let us move on now. Consider this situation where V is equal to mu1, mu2, which we just derived, 4 pi epsilon 0 r cubed 1 minus 3 cos squared theta, cosine squared theta. Now just looking at this, under what conditions can V, or if V tends to 0, what can I say about this? Can you tell me? Any factor I can say tends to 0? 1 minus, so see mu1 and mu2 cannot be 0, right, because we know they have dipoles, that is a given. If mu1 is 0, then obviously we are not going to talk about anything else. So but it's, so this one, that means 1 minus 3 cosine square theta should go to 0. So that means what you are trying to find out is at what angle, that means at what angle you would not be having any interactions between the dipoles. That is essentially what you are saying, right. That means if V is going to 0, so here I can write cosine square theta is equal to 1 by 3, or cos of theta is equal to plus minus 1 by 3. Now based on this, if cosine of theta is equal to root of 1 by 3, okay, then theta comes out to be 54.7 degrees, okay. See, in some sense this will come back to later in the course when we talk about fluorescence, but in some sense you can realize one thing. If you have two dipoles which are oriented at this angle, it is essentially a magic angle, right. That means you do not have any interactions. So then how does the potential picture look like? So what I mean is, suppose I have a dipole like this, again let me start from the center of the page. I have a dipole like this, right, and I am trying to find out regions where they are attractive and repulsive in terms of your V. So let this be the center, and these are two lines I am drawing. These are two lines I am drawing, okay. Now this angle is 54.7 degrees, okay, and say this is your dipole, this is q1, this is minus q1. So, you can understand one thing, if theta, the theta you are talking about, if theta is less than 54.7, that means if theta, so in this region from here to here, your V actually is less than 0. In this region your V is less than 0. Why? Because 54.7 is where interaction is 0, right? When you start from here, your interaction was attractive. You move like this, you move like this, you move like this, you go to 0, then beyond that you will go into the repulsive regime. So, between these two crosses or between these two lines, I can say this is V is greater than 0, right. Similarly here V is greater than 0, and then again you come on to the other side, you have V which is less than 0. Okay. So, this is a very nice picture which tells you how the dipoles, if they are oriented, what their respective nature of attractions or repulsions would be, or nature of potential energy would be, whether attractive or repulsive. Now, to explain it, that means if theta less than 54.7, then V of R or V essentially is attractive, right. If theta is greater than 54.7, as shown, V of R, because it depends upon R, is repulsive, and what about the angles at which you will not be having any interaction? So, one is theta is equal to 54.7, what is the other angle? 180 minus this, right, 180 minus this. So, the other one is at 180 minus 54.7, at 180 minus 54.7, right. This is another case where if this is your theta, here again V of R is equal to 0, like V of R is equal to 0. So, essentially this line and this line are what? Your lines of 0 interaction, that you can understand now, right. This line and this line are essentially lines of 0 interaction. So, what it means is, now start looking here, if I have say a charge which is say plus q2 here, right. Now, q2 is close to minus q1. So, obviously if you are in this regime, this q2 is closer to its opposite charge, hence obviously your interaction is attractive. Now, the moment you come here in the middle, what happens? This was a 0 line, but the moment you come here, you are coming slowly closer to what? q1. Now, these are like charges, hence your repulsive interaction comes in. So, that is how you can think about it. Okay. So, this was about the regions of your attractive and repulsive interactions, and also please keep in mind the different alignments you can have. So, if you would know that formula, then based on theta 1 to theta 1 and theta 2, you should be able to derive your interaction potential. That you should be able to do. The significance is, if anyone gives you a system like that, and because you would know V of R for any given angle, you would be easily able to calculate, because you know V of R, right. Okay. Now, moving one step further, let us think about this. We will go back to an ion dipole interaction, and I will tell you why. We are looking at it again. Yeah, the reason is this. See, when we if you would remember, we had a dipole like this, right, say q1 minus q1, right. This was L, the length of the dipole, and we had a charge out here, say q2, which was making a certain angle theta, right. And for this one, what was a V? Do you remember? It was, so if this is a dipole moment of mu1, then it is minus mu1 times q2, right. Then we had a factor cosine of theta, then we had 4 pi epsilon 0 r squared, and this is again squared because we are talking about a dipole interacting with an ion or vice versa. But think about a real life situation. if you have a freely tumbling dipole, would you be maintaining a single theta? You will not be maintaining a single theta. What you would instead be maintaining is a range of theta values, a range of theta values. So what we are going to do now is we are going to look at something known as orientational averaging. We are going to look at orientational averaging. That means theta has a wide range of values, and I will just tell you what the range is. So this is what we are going to look at, and you will be surprised what this orientational averaging can do to interaction. Okay, just wait for this. So look at this equation again, and let me write this equation again just to make the connection. I can write the previous equation as V of r theta, because it depends upon theta, it also depends upon r, to be equal to minus q mu1 q2 4 pi epsilon 0 r squared cosine of theta. Okay, and this I can simplify further by writing V of r theta is equal to minus V0 times cosine of theta, where see V0 is equal to, where V0 is equal to mu1 q2 by 4 pi epsilon 0 r square, or for a general case I can write, just write mu, I will remove the subscript 1 and 2, q by 4 pi epsilon 0 r square, right. This is a very general form, right. So remember out here, since we are involved in only the angular orientational averaging, our radial part does not come in. So it essentially comes into the constant V naught, because we are doing an orientational averaging with respect to theta. Now what do you mean by that? To find this orientational averaging, that means the potential coming from orientational averaging, we will solve an integral like this. We will solve V of r. See, I am not writing r theta anymore. The reason is because I am doing an orientational averaging, I am essentially integrating theta out, right. There is no longer any theta dependence, that is what I am doing. So this is equal to, now this you have to remember, okay. Let us look at the limits, 0 to pi, okay, V of r theta e to the power minus V r theta over kt, then you would be having sin theta d theta, and in the denominator you have this minus V of r theta kt sin theta d theta. So again, so this is your average V of r. So this is like your expectation value, this is your average value. V of r is equal to, the numerator is V of r theta, which you know, e to the power minus V, this is r, it is not V, it is looking like V, it is r theta by kt over e to the minus V of r theta by kt sin theta d theta, right. So this is your integration, that is integration variable. Now look at what theta varies. Theta varies from what? 0 to pi. So you can think about a dipole and an ion. So the dipole can say this is the angle theta, then the charge can go from here to here. And if you go the other way, you are just essentially repeating, that is what you are doing. But the charge can go from here, right, any theta, 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 and then it can go to the other side, right, covering an angle of pi, which is 180 degrees. So this is what we will have to solve, guys, and actually we are going to do that, right, we are going to do that. So how? We will make an approximation. First of all, we know that V of r theta is equal to what? Minus V0 cosine of theta, we know from before, right. We will also do one thing, we will say V of r theta by kt is much less than 1, is much less than 1, right. Do you understand the significance of kt here? You can realize this term has a temperature dependence. That means these forces would be dependent upon your thermal energy, and here thermal energy is reflected by what? The kt term or RT, whichever way you want to look at it. So based on these two, and especially this is an assumption we are making, okay. So if V of r theta by kt is much less than 1, then what I can write is, look at e to the power minus V of r theta over kt. So what is this equal to? This is equal to, I can write e to the power V0 cosine of theta over kt, right, because V of r theta is equal to minus V0 cosine of theta, and I already had a negative sign here, and I know this one is much less than kt. So what I do is, I do an expansion of this Taylor expansion of e to the power x. If I do a Taylor expansion of e to the power x, what do I get? I get 1 plus V0 cosine of theta over kt and so on, right. So I am making this assumption, and based on this assumption I am simplifying my problem, or we are simplifying our problem by expanding this in terms of the Taylor series expansion, and just we take the first two terms, 1 plus V0 cosine of theta by kt. So this is something you are now by this time you are familiar with, right. We did it for the iron dipole too, remember, 1 plus L by r or 1 minus L by r, and we do not consider the other terms, essentially the same thing we are doing. So take this and put it back in the integral, okay. But what we will do is, now we will look at the numerator and denominator separately, right. So let us look at the denominator. So let us look at the denominator of your integral. So the denominator is 0 to pi, again I am writing e to the minus V r theta by kt sin theta d theta, okay. So this is essentially again 0 to pi e to the power V0 cosine of theta over kt sin theta and d theta, and using the assumption which we have already done in the previous sheet, we can write this 0 to pi 1 plus what? V0 cosine of theta over kt, right, times sin theta d theta, and this I can further simplify as 0 to pi, I can write what is the first term, sin theta d of theta plus 0 to pi V0 cosine of theta kt, then I can write sin theta d theta. So you can see what we have done is, from a complicated exponential integral we have split it into two very easy to do sum of integrals, okay. So let us take these two integrals one by one, this one and this one. So 0 to pi sin theta d theta is equal to what? Minus cos theta in the range 0 to pi. Now tell me what the value is. Thank you. So the value is 2. Does everybody realize that? Okay, this is cosine of pi minus cosine of 0, minus 1 plus 2, okay, great. Now this was the easy one, right. Let us look at the other one is also very easy. See, the other one I am looking at 0 to pi V0 by kt, okay, cosine of theta sin theta d theta. V0 by kt is a constant, right, because we are integrating over theta, right. So though V0 has the term r, it does not matter to us because we are not even integrating over d of r, we are doing an angular orientation averaging, right. So r essentially is a constant. So then I can write it as V0 by kt, obviously kt is also a constant, 0 to pi cosine of theta sine theta d of theta. And let us do a trick, I am sure you guys know. Let x equal to, I can do that or I can also do this. Let x is equal to cosine of theta, right? Then what is dx equal to? What is dx equal to? Minus sine theta d theta. Okay. So this one, this integral, okay. So one more thing, if x is equal to cosine of theta at theta equal to 0, theta equal to 0 because I have to change the limits of x. What is x equal to? 1, right? At theta is equal to pi, what is x equal to? Minus 1, right? Yeah, there are many ways of doing this integral. So I am just showing one of the ways. You can even do it as you said. We can write this one as, let me look for your page. So we can write this one now as is equal to V0 by KT, right? I have a negative sign coming here. Then what do I have? I have 1 to minus 1. I do x. And look at this sine theta d theta. What is sine theta d theta? This is essentially d of x, right? I already have d of x. So I can put d of x. Now this is an extremely simple integral, isn't it? And what is the value of this integral? What is x dx? X squared by 2, and then what will you get? 0. Good. So this is 0. So this one goes to 0. Simple, right? So see, a very intimidating integral which was down to the denominator gives what? A value of 2 essentially. So the denominator is equal to 2. The denominator is essentially equal to 2, right? Good. If you are done with the denominator, what did we have in the numerator? So let us look at the numerator now. The numerator is 0 to pi v of r theta, right, e to the minus v r theta by kt sine theta d theta, right. That is what we have for the numerator. Now this, what was v r theta? I can write this one as 0 to pi. V r theta was minus v0 cosine of theta. So I can take the negative sign out here and I do v0 cosine of theta e to the power, what should I write here? I can write v0 cosine of theta over kt sine theta d theta. Okay, going step by step. Now this is equal to, guys, this is equal to minus 0 to pi, I can keep the v0 outside, I have cosine of theta, but this one is already simplified for me, isn't it? 1 plus v0 over kt, then sine theta d theta. And I do a further simplification, I can write it as minus v0, then open large brackets, here is 0 to pi cosine of theta sine theta d theta, right, plus 0 to pi v0 by kt sine theta d of theta. I missed one, isn't it? What did I miss? Did I miss anything? Just check. Okay, so what I missed in this case is cosine of theta out here. Okay. Now these are the two integrals you have to solve essentially. These are the two integrals you have to solve. If you are going to solve these two integrals, what are you going to get? So for the first one, what is it? The first one is 0. We already know. We did previously. So the first one is already going to 0. So then for the numerator we are left with, so the numerator again we are left with is equal to now minus, I can write v0 squared because I have a V0 out here, I can write V0 squared. Then what am I solving now? Okay, right. But if you go back to this again, actually I missed another term. I missed a cos theta, so I can just write cosine square theta here. Okay, otherwise it will also go to 0, which you don't want. Yeah, so that's my mistake. Okay, so coming again back from here, so minus V0 square, then I have 0 to pi cosine square theta sin theta d theta by kt. How do I solve this one? I actually do the same principle again. I allow cosine of theta to be x, right, and this would become what? I can write V0 squared over k of t, right. Then I can write plus 1 to minus 1 x square, then d of x, again putting x is equal to cosine of theta, right. See, we had a negative out here, right, and this negative is cancelled from here because of this. What do we get from here? V0 square by kt. Now I have, it's not x square by 2 anymore, right. What is it? X cubed over 3 plus 1 minus 1. What are you going to get? Tell me. This is minus 1 by 3, minus 1 by 3 again anyway. So I would be getting minus 2 by 3 V0 squared over kt. Okay. You should be feeling happy now. See what he started from. He started from a very fearful integral, right, and what did you get? The denominator was 2 and the numerator is minus 2 by 3 V0 squared over kt, and you know what V0 is, it is a constant. Okay. So let me combine. So combining numerator and denominator, then average of V of r is equal to minus 2 by 3 V0 squared over kt, and what did I have in the denominator? 2. So it is essentially minus 1 by 3 V0 squared over kt. Okay. What was V0 equal to? So I can write minus 1 by 3, then I can write mu 1. This one was q, right? I can just write mu q. Let's take out the subscript. I can just write mu q. Then what did I have in the bottom? 4 pi S70 r square. So this is essentially what? Whole squared over kt. I am just plugging in V0, right? You follow that, right? I am just plugging in V0. Look at this. What I can further write is as minus 1 by 3 kt. Okay. Then I can write mu q over 4 pi S70 squared. What happens to r squared now? It goes to r to the power 4. It goes to r to the power 4. And this is important. Goes to r to the power 4, and this is extremely important. So there are two important aspects. One is, you can see this V of r is going to depend upon T, because obviously your thermal energy is going to have an effect on your potential energy of interaction. Okay. And the second point is, because of orientational averaging, because of orientational averaging, now V of r is proportional to minus 1 by r to the power 4 when we had no orientational averaging, then V of r was proportional to what? Minus 1 by r squared, minus 1 by r squared. So again guys, please understand the implication of this, or the implication of this rather. The implication is one, your V of R definitely depends upon the temperature, because if temperature is too high, you are going to disrupt all potential energies of interaction, right, thermal energy too high. Second is, the moment you bring in orientational averaging, you essentially just square this term which was initially obtained from a constrained value of theta. Okay. Now, though I should be, I probably, this is where we are going to stop for the class today, but I mean let me tell you this. The one we derived for this dipole-dipole interaction, what was it? It was 1 by r cubed, right, for a fixed angle theta. So in that case also, if you bring in this orientational averaging, where will it go to? It will go to 1 by r to the power 6. Take this 1 by r to the power 6 and extend it to what you know in case of van der Waals interaction, the attractive forces. What was the last term? The last term was also r to the power 6. Do you remember the attractive term? You have, say, a by r to the power 12 minus b by r to the power 6. That also has an r to the power 6. And the van der Waals forces are essentially what? Induced dipole-dipole forces, right? And because you have induced dipole-dipole, see, it's still essentially dipole-dipole. And because you have a dipole-dipole, that attractive term is still r to the power 6. So hopefully I have not put you off too much by the derivation, but in some cases, the moment you do the derivation, you have a much better feeling about actually what is going on than just looking at a formula. And that's why we did this rigorously, and at any point of time we would have to do a derivation like this, you would be able to do it. Okay. So this derivation, the last derivation, you do not have to remember for the exam. I am not going to ask you this derivation, but what you should be remembering is the effect of this orientational averaging, and for ion dipole, dipole-dipole, what are the different dependencies on R. Okay, how the range changes from Coulombic R to R squared to R cubed, and then also R to the power 4 and R to the power 6 because of orientational averaging. Okay, good.